Last example here, we're going to be sketching this x to the 2 over 3 minus 1. So we've got this rational exponent, and we'll have to see what that actually looks like. Okay, so following the components of the curve sketching algorithm in my own personal way, I'm going to look for the domain, which in this case, because that is essentially saying a cube root of x squared, cube roots, I can cube root pretty much anything, so I have a domain of every real number. Nothing is restricted for me. For x-intercepts, where I want to know where this could possibly be a 0, notice how I've kind of rewritten this so that it was something squared. That way you can kind of see it as a difference of squares. So this is going to have these conjugates, which the only way that this could produce zeros is if x was a 1 or x was a negative 1. So I figured out a way to find x-intercepts. And then y-intercepts, when x is a 0, it's a negative 1. In terms of asymptotes, there's no way for me to have any vertical asymptotes because I don't have any restrictions. And then you could, if you wanted to, find that there's no horizontal asymptotes either, and the reason for that is because of just the taking the limit as x approaches infinity. This thing here, as x approaches infinity, is going to essentially just keep growing. Okay. For the derivatives that are going on here, if I take the derivative, the first derivative that's here, it's a fairly simple one for us to work with. That gives us no zeros in the numerator, but a 0 in the denominator, so I've got a critical number that's there. For the second derivative, let's take the derivative of this thing, or it's probably easier to do it in this way, which is kind of what I did. I took the negative 1 over 3, moved that down, and then just subtracted the exponent by 1 again. Again, I've got no zeros in the numerator, but I've got a 0 in the denominator, so I've got a possible point of inflection at 0. So it could be a local max or min, it could be a point of inflection, or it could be nothing at 0. So let's see what's going on. If I chart this thing out, then this is what's going to happen. For this first derivative that's here, the numerator is positive, the denominator is the only thing that can change signs. Let's look at the denominator. At 0 is where it's going to change sign, and that is the cube root of x. It's going to go from negatives to positives. The 3 really won't play a role. And then over here, the numerator is always negative, so my denominator, which is here x to the 4, and then I'm cube rooting it, but if I put any number into x to the 4, it's going to be positive. So no matter what I do here, I'm getting a positive number in the denominator other than 0. And my numerator is going to be negative, so this is why both of those are negative. And then summarize it. So here at x being 0, I had some undefined values, which is why they were critical numbers and possible points of inflection. And then you'll see why it's undefined, because of the shape that's here. What's going on at x being 0 is there is a cusp. These were both concave down. One was decreasing, one was increasing, but they've met at this point, which is our cusp. So if we actually plot the function out, then it should look something like this. Here are my x-intercepts. Here is that cusp, that was the local min, and then there's my concave down, decreasing, increasing.